I'd like to thank the organizers for the invitation. It's an honor for me to speak here. So the first time I remember that I met both Nessim Simoni and Jean-Pierre Demailly in summer school in Toulouse, maybe 1994 or 1995. And at that time, they taught me about so L2 technique and also dynamical system. And I didn't understand anything at that time, but except that this was a very important and beautiful topic. And I think it's maybe the most important thing to understand for master student at that time. Anyway, so today I'm going to talk about automorphism on compact Kähler manifold, and in this research direction, they are both L2 technique and dynamical system. So let me start with some notation. So let X be a compact Kähler manifold or a positive manifold of dimension n, and we denote by X the group of all holomorphic automorphisms of X. So by a classical theorem by Bochner and Montgomery, out of X is a complex Lie group of finite dimension, but it could be disconnected. So you have a connected component of identity. So it's odd 0. And you might have many components, but it could be a finite number of connected components or countable number of components. So odd 0 is a normal subgroup of odd X, and then you can consider the quotient, which is a countable or finite group. Yeah. So the group odd 0 is generated by holomorphic vector field on X, and our main problem here is to study the quotient. So odd X over odd 0 of X. So this is the topic of our discussion. Okay, so let me give you two examples, which are very simple to understand. So the first example is the following. So you take the power n of generic elliptic curve, e to n. So we see that odd 0 is just the set of translation on T, and odd T is generated by odd 0, and the automorphism induces by GL and Z, because here E is generic, but if E is not generic, then you have a little bit more automorphism. Yeah. So in this case, the quotient is GL and Z. Is the first example. The second example, you consider a projective manifold Z of dimension m, and you consider the product of Z with the first example. So we have a fibration. So Z is like that. And the fiber is just e to n minus r m. M is the dimension of Z. So you can check that, assume that Z is generic in the sense that the automorphism group is identity, it's trivial. Then you can check that the odd 0 of X is the set of translation on the fiber. Yeah. And now if you have rho K, a map from Z to E, then you can produce some new automorphism. So basically, you consider translation on X fiber, but when you change the fiber, the translation change also holomorphically, depending on Z, on the point Z. So the formula is given here. You have more examples by taking quotient, product, blow up, and then some other family of examples by Bedford Kim, Marc Moulin, Orizo Thuyen, and other examples by Orizo. So I'm not going to discuss all these more complicated examples. I will focus only on these two examples. Okay. So here's the first question, which is quite classical. The question is the quotient group we consider here is finitely generated or not. So the problem comes back to the work by Jean-Pierre Serre in 1950. The answer is actually yes for dimension 1 and many cases in dimension 2. So dimension 2 except when X is rational or birational to a K3 or a quotient of K3 surface. And recently, Lazard proved that for dimension 6, there is an example such that this quotient is of infinite, is not finitely generated. And moreover, this is a very related question. X admits infinitely many non-equivalent real forms. So for the second statement, you can, roughly speaking, when you have a real algebraic manifold, you can complexify it and get a complex positive manifold. But given a complex positive manifold, maybe you have different way to complexify real manifold to get the given complex one. And some of them are equivalent. For example, if you have one real structure and you have some automorphism, you can move it to another one. But you consider that these are equivalent. So like on P1, you have a real positive line, but you can move it by using some Mobius transformation and you get another, but they are equivalent. But here we consider non-equivalent real forms. So there are some examples such that you get infinitely many of non-equivalent real forms. So to prove this, we use particular automorphisms. This is the reason that there are some relation between the first statement and the second one. This is due to Jean-Pierre Serre and other people. So for every n larger or equal to 3, there is a rational manifold satisfying those properties. And we also show that in dimension 2, there is a rational surface satisfying the second property, or surface birational to K3 or enriched surface. So which means that for the second property, the question is, the solution is now complete because we know that for all other rational, other surface, we don't have such a property. Yeah? There is an open problem which is left here. So is there a rational surface with the first property? We don't know yet. So working with rational surface is quite difficult because when you blow up rational surface, you might have more automorphism or less. So it's difficult to control this. It's not the case for K3 surface. For K3 surface, when you blow up, you have less automorphism. So this is the main reason that the problem is difficult. But also there's other issues, like for example, in a rational surface, you can have rational curve like that, something like that, which pass by this point, many points. But everywhere you can have such a situation, but when you blow up it becomes smooth curve. So it's more difficult to handle rational surfaces. And this question is open. Okay. So now I'm going to talk about the entropy. So this is a classical notion, which is a little bit long to introduce here. So I skip the original definition, but give you some equivalent definition for this setting. And actually, Simone and myself, we introduced the entropy to this topic so some time ago. So let me first introduce this notion. So when you have an automorphism f from x to x, then you have the action of f on cohomology by Poulbach form, differential form. And dp is the dynamical degree of order p is just the spectral radius of F star on HPP. Okay, so you have some square matrix, and you just consider the absolute value of the maximum of the absolute value of eigenvalues. It's a dynamical degree, so it's quite easy to compute or estimate. Topological entropy is in general difficult to compute. It turns out that in this setting, due to Homov and Dinh, we know that the topological entropy is equal to the algebraic entropy. So you just take the maximum of log of dp, and this gives you the topological entropy. It's very surprising. So in particular, you see that the topological entropy vanishes if and only if dp is equal to 0 for every p, or you can show also that is equivalent to the fact that dp equal to 1, dp equal to 1 for some p between 1 and n minus 1. It's not difficult to prove this. A deeper remark is that this sequence of dynamical degree is first increasing, and then it might be stable sometime, and then decreasing. So this is due to some mixed version of Hodge-Riemann theorem that I'm going to talk later. And then you see here that the topological entropy is just equal to log dq, according to this notation. And you also see that if you are in the connected component of identity, then the entropy is equal to 0, because the action of auth 0, because auth 0 is connected, so the action on HPP, so you take, okay, maybe H real cohomology with coefficient in Z or in Q, and you see that this action should be constant. So then, because the action of identity is trivial, then for every one in this family, the action is trivial. So the spectral radius should be equal to 1, and log 1 is 0. Okay? So, so this is clear. Yeah. Okay, so now I can state another theorem due to many people. I mean, it's a combination of different theorems. So in particular, due to Campana, Wang, Zhang, and Zhang. So if you take any group of automorphism, G is a group of automorphism, and then you consider the intersection with the component of identity. So we denote it by Z0. Z0 is G intersect with auth 0. Yeah? So this is our notation. So this is a subgroup, a normal subgroup of G. So G divided by Z0 is a group also. Okay, and you denote by energy the set of elements of 0 entropy. In general, this is not a subgroup, because when you compose a 0 entropy endomorphism, automorphism, you can get positive entropy automorphism. So in general, it's not a subgroup. So the theorem says that either this group G over Z0 is very big, it contains a free non-abelian subgroup, or otherwise it's not very big, it's quite small. So if you replace G by some finite index subgroup, then NG become a normal subgroup. Okay, in general it's not a subgroup, but now it's a normal subgroup, and the quotient is a free abelian group of rank at most n-1. Okay, so you have, in the second situation, you have G0 is of 0 entropy, is contained in energy. It's a subgroup of all elements of 0 entropy, and is contained in G. And then the quotient is an abelian group free abelian group of rank at most n-1 is optimal. You cannot do better. If you introduce the collider dimension here, then you can have a slightly better estimate. But here, if you want something which is independent of x, the rank here, n-1, depends only on the dimension of x. It's independent of x. So then n-1 is optimal. Okay? And so this quotient G over Ng is the positive entropy part of our group. But now to study our problem, we need to study this group Ng. Ng is a group of 0 entropy. Yeah, there is also the problem of classification of X such that the rank n-1 here is the rank is n-1, which is optimal. It's maximal and optimal. Then the problem is still open, and there are many work by De Kizang and his collaborators, but the work is not yet finished. So I come back to the example, the first example. So I consider the action of S, L, and Z on the torus T, and you take a matrix G, and it's easy to check that this automorphism has positive entropy if and only if G has some eigenvalue of modulus larger than 1. It's easy to check. And actually, according to a theorem by Prasad and Raghunathan in 1972, this group admits a subgroup, abelian subgroup of rank n-1, which is conjugate to a group of diagonal real matrices. So because of this, you see that all elements of this subgroup is of positive entropy. Because otherwise, the diagonal element should be all equal to 1, minus 1, something like that. But then you have an example where the rank is maximal, so n-1 is optimal. You cannot do better than that. Okay, so now we study the group Ng is a group of 0 entropy. Okay, so let me, for simplicity, denote now G by a subgroup of odd X, and I assume that all elements of this group are of 0 entropy. Okay, so now I want to study the quotient G divided by G0. Okay, so I come back to the same example. So S, L, and Z act on this torus, and you have the unipotent group U and Z of upper triangle matrices like that, acting on T, and you see that all eigenvalues are equal to 1, so the entropy is equal to 0. The collider dimension is equal to 0. Yes, this is the first example. The second example, so the example of fibration that I considered before. But now I assume that Z is of dimension 1, so it's a Riemann surfaces. And here you have n-1. So in order to simplify the notation, we consider only one map rho from Z to E. Okay? So using rho, you can produce n-1 new automorphism by using some translation on each fiber, and you use the only translation on the factor number J, so xj plus rho Z, and you see that because of rho, the translation depends on the position of Z. So when you change Z, the translation changes holomorphically. Yeah. So you have a new automorphism, and also of 0 entropy. Okay, and then all these automorphisms together generate an action of the unipotent group UN/Z on X. This you can check this, and this is a group of 0 entropy. In this case, the codimension of X is equal to 1. So we expect that in those examples, you have the biggest group of 0 entropy. We hope that. We don't know because we don't know any other example. And then for the classification problem, we expect that we should be for the case where the 0 entropy group is maximal in some sense, we should have this example or some little modification of this example. But we don't know. This is completely open. So let me tell you what we can say about this automorphism. So here's the first theorem for the case of one automorphism. So you take any automorphism F from X to X of 0 entropy. So we know that the action of F on cohomology should have a spectral radius 1. So the eigenvalue has modulus at most equal to 1. Actually, it should be equal to 1 because it's invertible. So it should be of modulus 1. So then we can show that when you iterate, so Fm for us is the iterate of order m of F. So the action of F on cohomology is given by a square matrix. So when you iterate it, it's equivalent to take a power of this matrix, the power m of this matrix. And then you can measure the norm of this power of matrix. And this norm is bounded by m to p prime plus q prime times n minus 1. Okay, so the formula is a little bit complicated. So p prime is the minimum between p and n minus p. Q prime is the minimum between q and n minus q. So what you can see here is that the right-hand side is independent of x, n of f. It depends only on the dimension of x. Okay, so this is the key points. So you take any manifold, you can take any automorphism you have of 0 entropy, you have this estimate. Okay, which depend only on n. Okay, so this is important. So we can see this in another way. So you can see the action of m on HPQ as given by a square matrix, and then you use the Jordan form of this matrix. So we can have Jordan block, and the eigenvalue should be of modulus 1, and the maximum size of the Jordan block is not more than p prime plus q prime times n minus 1 plus 1. You cannot have bigger Jordan block than that. So for example, if p equal to q equal to 1, then you obtain this power equal to 2 times n minus 1, and this is optimal for p equal to q equal to 1. Okay? So this is about one automorphism. Now, this is the main theorem. So if you replace G by a suitable finite index subgroup, so modulo a finite index subgroup, then we have that the quotient G over Z0 acts faithfully on HPP XR for every p between 1 and n minus 1. Which means that you can identify G mod Z0 with the action of this group on HPP. Okay, you can identify this group with the action on HPP. If you know the action on HPP, you can identify the group. Yeah. This is the first part. The second part, which is more important, so the action on HPP is unipotent, and the derived length is at most equal to n minus 1. At most equal to n minus 1. So more precisely, they are a filtration of a subgroup of G. So here H0 is equal to G0, H1 is H1 contains H0 and so on. HL is equal to G. L is at most equal to n minus 1. And the quotient between Hi plus 1 and Hi is abelian. So which means that in general G is not abelian, but you can build G using G0 and less than n abelian group. You can build it step by step and get G in this way. Okay. Or another way to see that when you consider the derived subgroup, so you take the bracket between G and G, you get G1, and then you take the brackets of G1 and G1, you have G2 and so on. And after n step, you are inside G0. So this is another way to see this group. So the quotient G mod G0 is not very far from being abelian. Yeah, it's solvable group in this way. If you introduce a codera dimension to this problem, then you have a better estimate. L is smaller or equal to n minus the maximum between kappa x and 1. However, the estimate is likely not optimal except in a lower dimension. We expect that the best estimate is L smaller than log 2 of n plus 1. And because we have this in the examples. So we have more result for vibration or the case of maximal L, but I'm not going to talk about this here. So you can see that you can ask how to get something like a log 2 of n plus 1. I mean, so the question is still open, but we have some approach for this. So if you define the central sequence from G, so you define G0 equal to G. G0, I don't know, like that. And then you define, G0. And then you define G1 equal to the commutator of G0 and G. And you repeat it. So you don't put the same here. So for example, G2 is G1 and G and so on. So this sequence is normally longer than the sequence that I give here. But if you can show that the length of this sequence is smaller or equal to n minus 1, then this is probably optimal. And then you get as a consequence that L is smaller than log 2 of n plus 1 is no. So if you have this estimate, then you get you solve the conjecture here. Okay? So this is the way that you get log 2 of n. Not directly, but using another sequence of a filtration of G. Okay? Okay, so I'm going to the next section. So here I'm going to discuss some techniques that we use in this setting. So the first important theorem that we use is the Fujiki-Lieberman theorem. The Fujiki-Lieberman theorem tells us that if we consider OC of X as the set of automorphism F such that the pullback of some Kähler class C is equal to C. So some Kähler class is invariant by C. Then this group is a finite union of components of X. So you can see in this picture, so the whole group might have infinitely many connected components, but if you consider this subgroup, then you only have a finite number of components. So equivalently, if you take the quotient of odd C over odd 0, then you have a finite group. This group is finite. So you can always, if you have such a situation, you always, up to a finite index subgroup, you are in odd 0. This is the idea, okay? So, so this is the first theorem. And there is an extension of this theorem due to Hu, Zhang, and myself. We have the same statement, but for any C, a big class in HPP, you don't need P to be 1. You have to take any big class in HPP, then you have the same theorem. But what I mean by big class, you have some invariant strictly positive, strictly convex cone, any one, you take any invariant strictly convex cone, you take some element in the interior of this cone. So you can take the cone of positive closed form, or positive DDC closed form, or whatever, currents, positive closed current, positive DDC closed current. Then inside this cone, you take any C, you have the same theorem, okay, for any P. This is useful to work with higher degree cohomology, HPP. So as a consequence, the kernel of this morphism is finite. Yeah, this is a translation from the consequence of the theorem. And then if you replace G by some finite index subgroup, then you can assume that the morphism is injective. Okay, so this gives you the first statement of our theorem here. So this action is faithful if you replace G by a suitable finite index subgroup. Okay, so then you can identify the quotient of G by Z0 by the action on HPP for any P. Okay, so this comes from Fujiki-Lieberman theorem. So the second technique that we need is the Lee-Kochin theorem. So Lee-Kochin theorem that if you have a Zariski connected solvable group acting on some complex vector space V, then you have a common eigenvector. Okay? So it's an exercise if the group is abelian. If the group is abelian, it's very easy to do that. But if the group is solvable, you can still do that. Yeah. You have a common eigenvector. But Kuhn and Ogiso and De Zhang extend this theorem for cone. So assume that the group preserves some closed, strictly convex cone. Then you can find some eigenvector inside this cone. This is very useful for us because we are working with different cones in cohomology group. Okay? Okay, so now you see the strategy of our approach to both theorems. So I remind you the two theorems that I forgot something. Oh. So I focus on this theorem on the size of F acting on cohomology, and this theorem. Okay. So sorry, I still need one more theorem that I skipped this. So let me come back to this. So we need the mixed Horst-Riemann theorem. So let me remind you this classical Horst-Riemann theorem. So assume that C is a Kähler class. C is a Kähler class. And then you define the quadratic form of Q on H11. So Q is given by this formula. And here is, in my picture, is H11, is R. And then you define the primitive hyperplane. So this P, what is notation? Yeah, P is a primitive hyperplane in this cohomology group. Okay, it's given by this formula. So the West product of the integral of alpha with C to n minus 1 is equal to 0. Then alpha belongs to this hyperplane P. Okay, this is a hyperplane because of Poincare duality and so on. You have this hyperplane in H11. And the Horst-Riemann theorem tells you that the quadratic form of Q given by this formula, Q alpha beta equal to the integral of alpha beta, the same class C to n minus 2. So this quadratic form is negative, definite, on this hyperplane. So this is a classical Horst-Riemann theorem. Okay? So according to a theorem by Khovansky, Tessier, Kromov, and the final version is due to Viet An and myself, we prove that we have the same theorem if we replace power of C by the West product of different Kähler class. So instead of C to n minus 1, you can replace it by C1, C2, C3 up to Cn minus 1. And Cn minus 2 you replace by C1, C2 up to Cn minus 2. So you have the same theorem. And you have also a version of Horst-Riemann for higher degree cohomology, and you have the same also for those groups. So why is this important? Because you see in the last slide, so here, or maybe this one, Rencontres theorem. So we can produce invariant class, but the invariant class is not unique, and you have many invariant class, so you have to handle different invariant class. So this version is, mixed version is more useful than the first version. You have to handle different classes. Okay, so then now we have enough technique to have a rough idea of the proof. So the rough idea is the following. So we have the action of group on cohomology, and you have some invariant cone like a Neff cone and so on, and pseudo-expectative and so on. You have many invariant cone, and according to Kuhn-Ogiso-Zhang theorem, we can produce invariant class in this group. So because the class belongs to some cone, you have some positivity because the cone defines some notion of positivity. So now you use a Horst-Riemann theorem to get some negativity. Okay, of course this you have to take some limit and so on. So you could be in the boundary of the cone and so on, but then you get some vanishing property, and this is the key point to get the estimate, and that in the last theorem that I'm talking about. Okay, so this is a rough idea of all this theorem. Okay, so let me tell you a little bit more about the proof. So according to Fujiki Lieberman type theorem, we can replace G by a finite index subgroup, so you can identify G divided by 0 by action of this group on cohomology. You can see everything on cohomology now. Okay, so then inductively we produce some invariant class. So the invariant class LP are constructed in the following way. So L0 belongs to H00 is a trivial case. So S0 belongs to H00. and L1 is in H11, and so on. So for L0, you just take the function identically equal to 1, and you have a class, positive class, in H00. And then you consider inductively the product of LP with the nav cone. This product gives you a cone which is not closed in general. This is one of the difficulties that we have. But then you take the closure of this cone. So it's become closed, but it's still strictly convex, fortunately. And then in this way, you apply Lee-Cauchy type theorem by Kuhn, Ogiso, and Zhang, and you can repeat it, and you produce a sequence of nav classes. And then by considering the action on cohomology, you can produce a filtration of the cohomology. So you see that you define FP, the set of class C such that the product of LP with C is equal to 0. Okay? So actually, I didn't give you the exact definition, which is a little bit more complicated, but roughly speaking, is this one. And then you can also define HP as a quotient of H11 with FP. Is a set of G which is identity on this quotient. Okay, so according to the invariant filtration FP, you have a filtration of the group. So you have H0, H1 up to Hn minus 1, joining G0 to G. Yeah. So then by definition, the quotient HP plus 1 over HP acts faithfully on H11 over FP. And then using mixed Hodgman theorem, you can show that the norm of G to M is something like M square, which is optimal also, on H11 over FP. And this is a way that you measure the norm of the iterate of F in the first theorem. Okay? So we can then prove that the quotient HP plus 1 over HP is abelian. But it's more complicated, and we need to introduce two other invariant filtration. So Fi prime, which is larger than Fi minus 1, and smaller than Wi, and which is contained in Fi. This is very interesting invariant filtration of the cohomology that I think I don't have time to say more about this. But then using all this invariant, you can get can show that HP plus 1 over HP is abelian. But I think the construction should be more useful than that. Yeah. So I don't have time to tell you more. So okay. So I stop here. So thank you very much.
Well, thank you very much. Any comments, remarks?
Yes.
I have a question. Thanks for the talk.
Yeah.
I have a question about the result with Ogiso, Lin, and Zhang about your when your automorphism of zero entropy, then you consider growth rate of this automorphism acting on HPP.
Yeah.
You said that it grows like n to the p prime plus q prime times n minus 1, something like that.
Yeah.
And then you said that, yeah, it's this one. You said that it's optimal for in a case when p equals q equals 1.
Yeah.
So I'm wondering, what about the other case?
I think by duality, you can consider the case where p prime and q prime are almost maximal, but for the middle index degree, we know that it's not optimal. I think
You know,
so.
it's not optimal.
Yeah, and we don't know how. We can consider the example to see what is the expected
by torus.
upper bound, but we don't know how to prove this. It's open. It's also
Okay.
open question.
What is the upper bound?
What is?
What is your expected upper bound?
So the main problem is that we actually work with HPP, but mostly go from H11 to HPP by taking product and so on. And this doesn't cover all HPP.
Mm-hmm.
So we get some information, but not all.
Okay.
Then I think this is the point that we don't know how to solve this. But it's not optimal. Yeah.
Okay, thank you.
Are there any other remarks, questions?
Yes, I have one.
Yeah.
At the beginning of your talk, you mentioned the minimal model program.
Yes.
What is the relationship? What kind of ideas is the...
This is so we assume that the action, you have a maximum group in some sense acting on your manifold. Then, so this due to De Kizang and his collaborators. So you try to use a MMP, minimal model program, but in an equivalent way, because you are working with dynamical system. So you have the source X and the target. You have to modify them in the same way. So you have to show that you can do that to get, you can run the MMP, and then you go to some model which is easier to analyze this. And we hope that you get the classification in this way. So as far as I know, so maybe my collaborator can correct me that if you consider exam closer to abelian case, then it works quite well. But if you consider the setting which is close to rational manifold, is more difficult. Yeah.
Thank you.
Yeah.
Any other questions or remarks? All right. If not, let's thank the speaker again.
Okay. Thank you.